A black hole forms when a massive star undergoes gravitational collapse at the end of its life cycle. The formation of black holes is a fascinating and complex process tied to the life cycles of massive stars. Here's an overview of how black holes form. Here's a step-by-step breakdown of the process. Nebula. Stars begin their lives in vast clouds of gas and dust known as nebulae. Gravity pulls these particles together, eventually forming a protostar. Stellar evolution. A star spends most of its life in a stable state, where nuclear fusion in its core counteracts the force of gravity. Main sequence star. The protostar ignites nuclear fusion in its core, converting hydrogen into helium and releasing energy. The star enters the main sequence. This fusion process converts hydrogen into helium, releasing energy that supports the star against gravity. 2. The end of a massive star's life. Exhaustion of nuclear fuel. As the star ages, it exhausts its hydrogen fuel. The core contracts and heats up, causing the star to expand into a red giant. Intermediate stages. As the star exhausts its hydrogen fuel, it begins to fuse helium and other heavier elements, causing the core to contract and the outer layers to expand. The star may become a red giant or a supergiant during this phase, depending on its initial mass. Fusion of heavier elements. The star begins to fuse heavier elements like helium, carbon, and oxygen, continuing this process until iron forms the core. Fusion of iron doesn't produce energy, leading. Core collapse. For stars at least 8 times the mass of our Sun, the gravitational force eventually overcomes the pressure from fusion reactions in the core. Gravitational collapse. When the core's mass exceeds a critical threshold, around 2 to 3 times the mass of the Sun, gravity overwhelms. This leads to a catastrophic collapse, where the core contracts rapidly and outer layers are expelled in a supernova explosion. Collapse compresses the core into an extremely dense point. Core collapse. Formation of a black hole. If the remaining core has sufficient mass, approximately 3 times that of our Sun, not even neutron degeneracy pressure can stop the collapse. The core continues to shrink until it forms a singularity, a point of infinite density, and the gravity becomes so strong that even light cannot escape into an extremely dense point. This collapse compresses the core energetic events in the universe. Event horizon. The boundary surrounding the singularity is called the event horizon. Gravitational collapse. When the core's mass exceeds a critical threshold, around 2 to 3 times the mass of the Sun, gravity overwhelms all opposing forces and the core rapidly collapses. Once any matter or light crosses this threshold, it cannot escape, rendering the black hole invisible. Outer layers ejected. The collapse of the core often triggers a supernova, a catastrophic explosion that ejects the star's outer layers into space. This explosion is one of the most. Observing black holes. While black holes themselves cannot be seen directly, their presence is inferred through their interaction with surrounding matter. They can affect nearby stars and gas, and X-ray emissions from accreting material can provide strong evidence of their existence. Core remnant. If the remnant core is sufficiently massive, it continues to collapse under its own gravity, forming a black hole. Summary. In essence, a black hole begins as a massive star, undergoes fusion and expansion, collapses due to gravitational forces, and forms a singularity with an event horizon where nothing, not even light, can escape. Scientists use indirect methods to study these fascinating cosmic objects. Singularity. The collapsing core is compressed to a point of infinite density, known as a singularity. Don't forget to subscribe to the channel and activate the bell to receive everything new.